Hello, welcome everyone. My name is Stefano Marin, and today I'll be talking about structure in the energy-dependent event-by-event Newton-photon multiplicity correlations in the spontaneous fission of californium-252. These are the authors, the University of Michigan authors of this research, but of course, this research wouldn't have been possible if we only worked within the university. I'd like to first of all thank all the collaborations that we have had throughout the years in performing this research. The lab that we collaborate with range from Oak Ridge National Lab, Los Alamos, Lawrence Livermore, Berkeley, Argonne, as well as the CA in France. All of this lab provided us with invaluable help, either experimental work, advisory work, or theoretical research. Now, moving on to the topic of today's presentation, the motivation for this work is the research and the investigation of signatures of special nuclear material. Special nuclear material, of course, being material that is of interest to the non-proliferation community for being able to undergo spontaneous or induced fission. Now, most of the products that come out of fission are charged particles and therefore are very easily shielded. However, the neutrons and the gamma rays coming out are actually cannot be easily shielded and can be detected even in in-field applications. In order to identify and even characterize some special nuclear material, we can use the correlations or the characteristics of the neutron and photon emission, and this is the goal of the group here in Michigan. One of the things that we do is to design detector systems that are very sensitive to certain aspects of the neutron and gamma ray emission. For example, this one, the issue here is the FS3 system currently in Michigan. In this case, you see that the detectors surrounding the fission source are can detect the presence of neutrons and gamma rays and find correlations between them. A second source of correlation, a second source of motivation for this work is the validation of phenomenological fission models. These phenomenological models that can help us determine the properties of the radiated emission in the cases where no experimental work exists. And fission, being a very complicated many-body nuclear reaction, actually has a lot of areas that are still not fully explored by experiment. Lastly, there is a component of basic nuclear science to the work we do, because we're investigating really the initial properties of the fission fragments as a function immediately following the fission reaction. And there is still a lot of interesting physics that have not been explored in this area. In the previous slide, I mentioned the presence of correlations in the neutron-photon signature. In this slide, I want to explain some of the most important sources of neutron-photon correlations, starting from a simple picture of the fission process and the emission of particles. First of all, we should understand that fission fragments are created in a variety of initial conditions following fission, and this can be described by specifying their internal excitation energy and angular momentum. These two properties together describe quite well the initial properties of the fragments. And as you can see from the figure on the right, the shaded ellipse represents all the initial properties that a fragment might take, which are then going to be de-excited by a sequential emission of neutrons and gamma rays until the fragment reaches the origin of this plot, or somewhere close to it, which represents the ground state. Now, there are the most important sources of correlations between the multiplicities of neutron and gamma rays can be split between direct and indirect. Direct sources of correlations are probably easier to understand. For example, decay competition. This is the classic case in which a fragment or a nucleus wants to de-excite by two different ways, for example, neutron emission and gamma emission, with some branching fraction between them. Then we expect there to be complete competition between the two modes. Another way that the fragments might de-excite is because they're both dissipating the same properties of the fragments. For example, neutrons and gamma rays both carry excitation energy, and therefore if more neutrons are emitting more of the excitation energy of the fragment, there is just simply going to be less overall energy for the emission of gamma rays. a bit more abstract and complicated are indirect correlations, where neutron and gamma rays are not correlated to one another, but they're both correlated to the same fragment properties. In this case, these fragment properties could be the temperature of the fragment or simply the initial energy of the fragment, which usually makes both particles of higher energy, or the angular momentum of the fragment, or the correlations also that exist between energy and angular momentum. These type of correlations tend to introduce positive sources of correlations. We should furthermore distinguish between two types of correlations that can exist when we combine together the knowledge that there are two fragments. So, of course, in the majority of fission reactions result in the appearance of two fragments, binary fission. And we might expect intuitively that the neutrons and the gamma rays are correlated when they come from the same fragment. And this is called intra-fragment correlation. However, there is also the possibility of interfragment correlations, when neutrons from one fragment are positively correlated or correlated in any form to gamma rays from the other fragment. And this can happen quite a lot, if the two fragments are very strongly correlated at emission. So if the two fragments are mirror images of one another with respect to energy and angular momentum, then we expect interfragment correlations also to be very strong. We will see that a lot can be concluded about the fragment correlations and also the correlations between the neutron and gamma rays simply by looking at the fluctuations in the multiplicities of particles. Well, having discussed the sources of correlations, it is now important to understand how to quantify them and to find where certain areas might have stronger correlations, weaker correlations, rather than just finding the sign of this correlated behavior. Well, a natural choice to do this is to look at the covariance, a very popular parameter that takes in two lists of values and describes the correlations in the fluctuations between them, the linear correlations specifically. In one case, we can start off by thinking that we have two lists of numbers, for example, the neutron multiplicity and the gamma ray multiplicity for each recorded fission event. This can be a very long list of values. And the first thing that we do to improve this parameter and make it more suitable for our work is to differentiate this with respect to energy. For example, as you can see here, we've taken this list of numbers, and instead of saying that there were 3 neutrons in the first event, we can say that there are now 2 neutrons in the first event, 2 neutrons of a certain energy, 1 neutron of another energy. And we can do this for each and every single history in this file, or every fission event. We do the same also for gamma rays. Now, to compute the energy differentiated covariance, we simply take the covariance between any two of the columns of the gamma ray multiplicity and the neutron multiplicity to compute this energy differentiated covariance, as indicated here. However, we should also note that the covariance between two lists scales with the total number of particles, so scales with the multiplicity. So therefore, we might find that the covariance at a very high energy, where there is not a lot of neutrons or photons, is naturally lower than one at lower energies, where we might expect higher yield. And this really doesn't indicate anything about the correlations between the two particles, but more about the population. So in order to fix this, or in order to really isolate correlations, we standardize, or we normalize the correlations by dividing it by the spectrum, as indicated in this equation. Now, this is a bit different from the more standard Pearson scaling, where we divide by the standard deviations of the two columns being taken, and but still retains very interesting property. The first one is that this parameter here, which we call CEN, E gamma, is semi-bounded, so it has a boundary of -1, indicating complete competition, and it's also invariant under efficiency. So different systems with the same sensitivity to different energy region, but different coverage, will naturally converge to the same quantity. Now, to apply this parameter to actual data, we are analyzing data collected at the KAINU array at the Los Alamos Newton Science Center. The array consists of 54 organic scintillation detector, EG309 liquid organic scintillation detectors, as shown here in an MCMP rendering, as well as here in a picture of one detector. Now, this detector system was actually designed for neutron detection, but it's well suited for the simultaneous investigation of neutron and gamma rays, thanks to the very good capabilities of these detectors to discriminate between neutrons and gamma rays using PSD. Well, after collecting all the data and analyzing 10 billion fission events, we finally can present the results of our investigation. As I've shown in the previous slide, the covariance after differentiation can actually be presented as a surface, where now the covariance for each energy beam is for a combination of neutron energies and gamma ray energy can be represented as a matrix or a surface. Well, something very interesting immediately pops up just by looking at this surface here, the appearance of these large positively correlated covariance at these intermediate photon energies. So we can see that there is a structure that appears between 0.7 and 1.3, 1.2, 1.3 MeV of gamma ray energy, and it persists throughout all neutron energies. This is actually something that is not expected. One way to analyze this and get a better understanding of the behavior is to take slices of the constant neutron energy and look how the correlations change with photon energy. And this is done in the panel on the right. As you can see, the black curve is the experimental data, and it's being compared with three model calculations, or theoretical model calculations by Freya, Friedlin, and CGMF, developed respectively at Lawrence Livermore and Berkeley, CA in France, and Los Alamos National Laboratory. There is a lot of things that we can describe about this, but what I wanted to focus on is the differences that the experimental data has with all the model calculations, because that's really what we're interested in, is to find what is currently beyond the reach of model calculations. Well, there are two regions that we can focus on. The first one is the absence of strong positive correlations at high gamma ray energy. And the second one is this appearance of this first peak at 0.7 MeV, which is actually quite absent or very low in magnitude, in amplitude, in the model calculations. Now it turns out, and there's a lot of analysis that can go into this, but it turns out that one of the ways that we can explain both of these behaviors simultaneously is by foregoing the assumptions that there are strong correlations between interfragment correlations, so between neutrons and gamma rays emitted from different fragments. And therefore, we reach our conclusions that our observations indicated that the dominating sources of correlations are interfragment, which is also intuitive, but is not predicted by model calculations. Now, this is actually something that we're working on with the theoretical groups throughout the US and national labs and also internationally to figure out how to explain this lack of interfragment correlations and what this means about the correlation between the two initial fragment conditions. So the expected impact of this work is that, as we said, we're continuously working with theory groups and national labs, and definitely the phenomenological description of fusion is a continuously evolving field with papers published every year with new and new aspects of the fusion process being presented. I would like to point out that probably two of the biggest unanswered questions in fusion right now are what are the production of angular momentum and how the energy of the fusion fragments is shared at scission. And these are something that we're also looking towards answering in the next few years. And I will also finish off by saying that the collaboration with national labs are definitely an integral part of the experiment that we performed, as well as the analysis that we performed in the experimental data. The next step of this work are going to be collaborating with Argonne National Lab and a few other universities and national labs to develop a new system that will be some of the most advanced system to measure fusion signatures. In this case, this would be the combination of three independent measurement systems: a fragment detector, the gamma sphere, a very powerful gamma spectrometer, and the FS3 system at the University of Michigan, which is a neutron and gamma ray detector. When taken together, this system is going to provide all the different correlations between neutron and gamma rays and give us unprecedented insight into the initial properties of fission fragments. Lastly, some of the other work that we're performing is also on similar data that I want to present today, but exploring other ways in which the covariance can be differentiated, other ways to analyze the correlations. And one posted by Owens and Severo, I was presenting also at this symposium, is about the directional correlation, so combining together both energy and direction to find a kind of phase-space characterization of Newton gamma correlations. And with that, I would just like to thank the consortium for all the support, and I'm open to any questions.